Have you ever wondered what happens to planets after their stars die? We know stars live for billions of years. They shine, evolve, and eventually collapse, often in dramatic, violent ways. But what happens to the worlds that once orbited them? Are they destroyed in the chaos, or do they somehow survive? Well, recently astronomers found an answer. And that answer was colder, quieter, and more mysterious than anyone expected. Meet WD 1856b, a planet about 6 times the mass of Jupiter, orbiting a dead star, a white dwarf, just 81 light-years away from us. A frozen gas giant drifting in the aftermath of stellar death. And thanks to the James Webb Space Telescope, we now know it is the coldest exoplanet ever observed. But what really makes WD 1856b fascinating isn't just its temperature. It's the fact that it exists at all. Think about it. White dwarfs are the ashes of stars like our sun. When a sun-like star dies, it expands into a red giant, scorches its inner planets, and finally collapses into a white dwarf, a dense glowing ember no larger than Earth. Most planets are expected to be obliterated during this process. But WD 1856b, it's right there, orbiting its stellar remnant like nothing happened. How? Why? And what does that mean for the future of our own solar system? In this video, we'll explore the incredible survival story of this icy planet, the cutting-edge technology that revealed its secrets, and why it may hint at habitable zones around dead stars, something once thought impossible. Stick with me, we're just getting started. To understand how strange WD 1856b really is, we need to talk about white dwarfs, the stars that come after stars. A white dwarf is what's left when a medium-sized star, like our sun, reaches the end of its life. Over billions of years, it burns through its nuclear fuel, swells into a massive red giant, and then sheds its outer layers into space. What remains is a white-hot core, about the size of Earth but with half the sun's mass. It's incredibly dense. A single teaspoon of white dwarf material would weigh several tons. No more fusion, no more light generation, just a fading ember, cooling over trillions of years. It might sound peaceful, but what happens during that death is anything but. As the star expands into a red giant, it can swallow up inner planets, just as the sun is expected to engulf Mercury, Venus, and possibly Earth in about 5 billion years. It can blast its system with intense radiation, destabilizing or ejecting other planets from orbit. That's why most scientists believed that no planet could survive the death of its star, especially not in a close orbit. But WD 1856b proves them wrong. It's not just surviving, it's hugging tightly to its host white dwarf, orbiting once every 1.4 days. That's 34 hours per year. Let that sink in. How did it get there? Was it always in that position? Or did it somehow migrate inward, long after the star had died? The very existence of this planet opens the door to new theories about orbital mechanics, stellar death, and planetary survival. And that's where the James Webb Space Telescope comes in, with the ability to see the cold, the faint, and the far. To unlock the secrets of WD 1856b, scientists turn to the most powerful space observatory ever built, the James Webb Space Telescope, or JWST. Launched in 2021, this telescope was designed to look deeper, farther, and colder than any before it. And in 2025, it turned its eyes, or rather its infrared sensors, to WD 1856b. Using the mid-infrared instrument, MIRI, astronomers aim to do something incredibly difficult: directly detect the light from a planet. Now that might not sound impressive at first, but here's the problem. Planets don't shine, they reflect, and compared to the blinding glare of their host stars, they're invisible. That's why most exoplanets are discovered indirectly, by watching their stars dim slightly as planets pass in front of them. But in this case, the star, a white dwarf, is so dim that it gave astronomers a rare opportunity. Using the infrared excess method, they captured subtle heat signatures from WD 1856b. And what they found was astonishing. The planet's atmosphere measured just 186 Kelvin. That's 87 degrees C or 125 degrees. That makes it the coldest exoplanet ever observed. And if that weren't enough, JWST data also helped revise the planet's estimated mass. Earlier predictions put it at 13.8 Jupiter masses, borderline too massive to be called a planet at all. But now, we know it's no more than 6 times the mass of Jupiter, firmly in the super Jupiter category. So what does this mean? Not only did this frozen giant survive the death of its star, it's cold enough, stable enough, and close enough to possibly exist in a new kind of habitable zone. But could life exist there? Let's explore that next. Let's get one thing clear. It's a gas giant, not a rocky world like Earth. It doesn't have a solid surface. Temperatures are far below freezing, and there's no confirmed atmosphere rich in life-supporting chemicals. So, no, this planet itself probably doesn't host life. But that's not the end of the story. Because if a giant planet like WD 1856b can survive and even migrate into a tight, stable orbit around a white dwarf, then maybe smaller Earth-like planets can too. And if they do, they could orbit within the habitable zone, the region where liquid water could exist on the surface. Here's why that matters. White dwarfs, while dim, are stable and long-lasting. They can continue radiating gentle warmth for billions, even trillions of years. Imagine a rocky planet orbiting just far enough to avoid freezing, but close enough to stay warm. With the right atmosphere and conditions, it could remain habitable for eons. Now think about moons. If WD 1856b has any large moons, and many gas giants do, they might lie within a temperate range, warmed by both the white dwarf and tidal heating from the planet's gravity. Such moons could have oceans, atmospheres, even weather, and they might be easier to detect than rocky planets themselves. In the future, missions using JWST and its successors could analyze the light spectra from these planets or moons, searching for biosignatures, oxygen, methane, water vapor, signs of possible life. We're not there yet. But the existence of WD 1856b makes that vision just a little more real. And there's one more reason this matters. Because one day, the sun will die too. The sun, our star, is about halfway through its life. In 5 billion years, it will run out of fuel. It will expand into a red giant, swallowing Mercury and Venus. Earth may be next. Even if our planet escapes engulfment, the sun's death will strip away our atmosphere, boil the oceans, and scorch the surface. Eventually, the sun will collapse into a white dwarf, much like the one orbited by WD 1856b. So the big question is, will anything survive? Until recently, most scientists would have said probably not. But now, with the discovery of WD 1856b, that answer has changed. Here's a planet, massive, intact, stable, surviving right next to a stellar remnant. It may have formed far away and migrated inward after the star's death, or it may have never left. Either way, it means that planetary systems may have second lives, that worlds can outlast their stars, that evolution doesn't stop when the light goes out, and maybe, just maybe, life too can find a way to adapt. So next time you look at the stars, remember, you're not just seeing suns. You're seeing stories, beginnings and endings, violence and survival, and planets silently orbiting in the shadows. Somewhere out there, in the cold, quiet light of a dead star, another world might be watching its second sunrise. And maybe someday we'll visit them, or become one of them. If you enjoyed this story, don't forget to like, share, and subscribe. And leave a comment. Do you think life could survive the death of a star? Until next time, keep wondering and keep looking up.